Good morning, theoretical chemistry. Hope you are having a wonderful day and you are incredibly excited for your fabulous Friday. Now, I want to start today with kind of a hypothetical situation, if you will. Let's say I handed you some marbles, and aside from saying I would have lost my marbles, let's say I asked you a question about those marbles, and I said, okay, if 4 of those marbles I handed you were red, and 3 of those marbles I handed you were blue, could you tell me what percent of the total number of marbles were red? Well, I imagine you would go, well, that's a lot like finding my quiz score. Let's say I've got my total here being 7 marbles. I'm interested in the red marbles, or the number right, if I were taking a quiz. To find your percent, you take the part you're interested in, divided by the total, and get your percent. So here we would find total number of marbles is 7, take the part we're interested in, divided by the total, multiply by 100, and get 57% of these 7 marbles are red. Now, we can take those same 7 marbles and change it just a little bit. Now, let's say I handed you these 7 marbles, and each marble had a particular mass. And those red marbles were actually now 7 grams each, and the blue marbles were each 5 grams each. And I want to know kind of the same thing. What percent of the total mass comes just from the red marbles? Well, okay, we got this. If we want to find the percent, we need to find the total mass of all of the marbles. If we're interested in the mass from the red marbles, we then find the mass of just the red marbles. Take the part we're interested in, the mass of the red marbles, which for this it would be 4 times 7 grams, that's 28 grams, divided by the total mass, which would be 28 plus the 15 grams from the blue, and then multiply by 100. For us, that would give us a percentage of 65%. Of the total mass here comes just from the red marbles. And I know what you're thinking. Mr. Jorgensen's being weird again. Because other than one day out of this entire year, we have never even touched a marble. What does this have to do with us? Well, we're in Unit 5. Unit 5 is about nomenclature. We haven't been working with marbles. We've been working with compounds. We've been naming different types of compounds. Acids, hydrocarbons, molecular, ionic. Now we can analyze these compounds in a slightly different way. Before we were naming them, now we're going to analyze them. What are they made up of? So let's apply this to compounds. Well, compounds, they don't necessarily have a number of marbles, but they do still have a mass. We call that, I hope somebody said molar mass. Yeah, we call it the molar mass. The molar mass of our element comes from that periodic table. It is the mass. This is a little bit of review. The mass of 1 mole of a substance. So let's say we had 3 compounds. And here are 3 compounds. We've got calcium hydroxide, magnesium phosphate, dinitrogen pentaoxide. All right. Before we can find the molar mass, though, we need to know how many of each type of element are in these compounds. We have to write some formulas. All right. So go ahead, take a minute, write some formulas. All right. Now that you've written the formulas for calcium hydroxide, magnesium phosphate, and dinitrogen pentaoxide, we need to find the molar mass. Now, if you remember, to find the molar mass of one element, we add up all the masses from the periodic table. So we would have, for calcium hydroxide, we would have 1 calcium plus 2 oxygen plus 2 hydrogen. Remember, we've got calcium hydroxide, Ca parentheses OH parentheses 2. Right? Once we've added up all those masses, we get the molar mass. Remember your units. The mass of a mole, grams per mole. I apologize, that last value is N2O5. It's 108.01 grams per mole. Well, cool. Now that we know the molar mass, we can find of that whole compound what comes from just a single part of the element. So, if we wanted to use this as an analytical tool to start to analyze our compounds more, we call this percent composition, the percent that a certain element gives to the total composition or the total makeup of our compound. By definition, this percent describes the relative mass each individual element contributes to the mass of the whole compound. To find the percent composition, it's identical to what we just did. We're going to take the mass of the element we're interested in, divided by the total mass of the compound, and then multiply by 100. Only we're going to use slightly different words. We're going to use molar masses. For us, we're going to take the molar mass of that one element in the compound, and we're going to divide by the total mass of the compound, which we just found, it's the molar mass, and then multiply by 100. So that bottom number there where it says mass of the compound, that's actually your molar mass. Okay? So we're going to take the mass of our element we're interested in, divide by the molar mass, multiply by 100. This will give us the percent composition. How you feeling? Let's give it a shot. So here's our practice question. The formula for glucose is C6H12O6. What is the percent composition of each element in glucose? And here in parentheses it tells us we are looking for 3 significant figures. Well, we know that if we're looking for the percent composition, the percent of the whole, we're going to need to find the molar mass. So we're going to go to the periodic table and we're going to add them all up. We've got 6 carbons plus 12 hydrogens plus 6 oxygens. So average time of mass for carbon is 12.01, I think. Pretty sure, last I checked. 12.01, we've got 6 of them. So 12.01 times 6 plus the mass from hydrogen, which is 1.008 times 12, plus the mass of oxygen, which is 16.00 times 6. We add all those up together and we should get the entire molar mass, which for this should be 180.096 grams per mole. Ooh, I left off my moles. That's minus 1/2. My units are off. I apologize. So that should be grams per mole right there on our molar mass. Now, as we look at this compound, there are in fact 3 different elements that compose this compound. We've got a carbon, we've got hydrogen, and we've got oxygen. 3 different types of elements. That means we're going to need 3 percentages when we're all done. We should have a percentage of carbon in there, a percentage of hydrogen in our compound, and a percentage of oxygen. So we set up 3 separate problems. We start with the carbon. What is the total mass from the carbon in this particular molecule? Well, carbon, there's 6 of them. Each one has a mass of 12.01. Multiply those 2 together, you get the mass of just the carbon. We want to know what percent that mass has of the whole mass, that 180. So we're going to take that mass, which is 12 times 6, divide that by the 180, multiply by 100. That will give us the percent composition of carbon. Now remember, 3 significant figures. When we do that, we should get 40.0%. Again, here's the mass from just the carbon, 6 times 12.00 or 12.0001, divided by the total molar mass, which was 180.096. To make a percentage, we multiply by 100 to get our 40.0%. We would do the exact same process for the other 2 elements. Now, the mass for those elements will change, but the total, the bottom number, won't change. The bottom number will always be the molar mass of the entire compound, 180.096 grams per mole in this case. Okay? So you'd repeat this for your remaining elements. Okay? We would find the mass from the hydrogen, divide by 180, find the mass of just the oxygen, which would be 16.00 times 6, divide by 180.096 grams per mole, and then we should have all 3 of our percentages. Our percent from carbon, percent from hydrogen, and our percent from oxygen. This is an additional analytical tool. This is another way that in the lab we can start to analyze what our different compounds are made up of. Not just naming them, not just writing them, but also analyzing what is in our different compound. Now that I've tried one for you, you try one for me.